Okay, cool. So let me share my screen. Can you also see the presentation, whichever I'm showing,
Yes.
sharing? Thank you. We can get the session started. Let's give everyone some time to join the call. Part of emerging digital technologies. Um, Couple of the what do you call uh, housekeeping rules on this one. I would like to have the session as interactive as possible. During the presentation, if you have any questions, feel free to stop, either unmute your mic and you can speak, or you can actually type in the chat, where I'll be regularly looking at the chat messages. And I personally believe that this session will be much more fruitful for each and every one of you if you are able to converse and raise good questions, whichever you get along the way. And let's keep the session as interactive as possible. Don't hesitate and keep asking the questions. And second things is like morning, I had another session with another group. They had troubles in accessing the chat. Now I think everyone should be able to access because we changed the settings. So just in case you are having troubles, just unmute yourself and just let us know. So yeah, let's get started. Today's session is going to be an introductory session on digital twins. Before we go into the details about the session, one important question you need to ask to yourself and to me as such is like, okay, you're talking about the session, so why should we listen? Like, do you have any experience or expertise in the same? So just to speak a little bit about that, I have a PhD in the field of optimization from National University of Singapore. I also have an executive MBA from INSEAD, I think second or third best global B school. Apart from that, the more important reason for this one is I actually teach the digital twins course for masters and PhD students in Singapore local university, university called as Singapore University of Technology and Design. I teach this course for a semester, so it's a 14-week course which I teach to students. The biggest challenge today will be that to condense all of this 14-week course into roughly about a 2 hour 45-minute session. I'll try my best to touch at least the core concepts such that you will be equipped at least to understand these concepts when someone points out this in digital twins. So as I said, let's make it as interactive as possible. So going first, so let me look at this. Okay, let's first answer this simple question. So everyone, please scan this QR code and type in and try to answer this question. What is a digital twin? Now, what am I trying to do with this one? So to create a word cloud, to understand what the audience in the session or the students in the session have heard of digital twins, have learned about digital twins in the past, anything in that rhythm, which will help me set up the expectations and also try to address the points better in the session. So please feel free to actually scan this QR code and type in the answer to the question, what is a digital twin? Let's do this for 5 minutes. I think there are about 19 of you in the call, so I expect some responses, good enough responses to form a good word cloud. And based on the emerging theme, we can discuss this further. So yeah, let's spend 5 minutes on this one. Okay, we are having good enough responses. No, uh, hello is a very surprising one present there, but remaining others are quite in the thing, right? So, digital replica is one thing. Carbon copy of a physical thing. Okay, that's a decent one. Simulation of real world, close to it. Someone may say something in the chat. As if it happens sometimes. Yeah. Virtual replica is something which is very close to a digital twin. We'll cover something about this particular theme in the actual definition a couple of minutes later. Um, uh, so yeah, the emerging theme is around that either a virtual replica or a digital clone in that direction of it. You are close to the actual definition. There will be certain caveats which we'll be learning more while we do the definition as such. So let's go and see the exact definition now. So you can see my. Can you people see my screen?
Yes, sir.
So let's start with the IBM definition of what a digital twin is. As per IBM, the definition of a digital twin is it is a virtual representation of an object or system that spans its entire life cycle and is updated with real-time data, uses simulation, machine learning, and analytics to aid in decision making. If you ask me what is the key word in this entire definition, I would start in this order. The first keyword is decision making. So a digital twin, the cornerstone definition of it is it has to help in decision making. So if you find a sophisticated tool which is called a digital twin by someone in the future, if they are not using that tool for decision making process, then it is just an expensive simulator. That's it. The core idea for creation of digital twins is to help in decision making in a better fashion. Second important thing is, like many of you mentioned, the virtual representation part. So the virtual representation or the virtual replica, it can be a 3D model, it can be a simple code of a system whichever is represented, or it can be a simple physical object which is being represented as in a simulation side of things. The virtual replica is also essential. Now the third important one is real-time data. So when I tell real time, right, in this particular context, I do not mean that you need to have data updated every microsecond, millisecond, or nanosecond range. Rather, it basically says, let's say the data is generated by your physical system in once every week or once every month. Once the data is generated, it has to be updated in the digital twin. That is what we say as real time in this context. The context saying that you can have the data upload once every week, once every month, once every year. If you are looking at it, it can still be a digital twin as long as that is how the data is being generated in your physical system. It can also be that, for example, right? Let's say we are talking about traffic flow. Traffic flow, we can have a cadence of probably seconds, which should be sufficient enough to call it a digital twin. But let's say we are talking about life cycle of a potato, which might take much longer time to replicate, which will have longer span. You can also look at if you're trying to replicate a nuclear power plant, where the data will be provided almost every microsecond and nanosecond time range, compared to some other places where data will be only updated once every week. A digital twin can be still created out of the system as long as you update the data as soon as it is being generated in the physical system. That is the only constraint there. Now, all this in this hierarchy is good, but the final one, which I would consider as the brain of the entire digital twin, is the usage of analytics, machine learning, artificial intelligence, or traditional data analytics, whichever you can call, or whichever tool you want to use. All of this is used to develop and do, let's say, predictions or do a forecast, or let's say help in decision making. So this actually forms the brain of the entire digital twin. Obviously, we'll go into much more deeper details about this, but understand in this order. Always decision making, then the virtual replica, then the data should be in real time. Finally, usage of analytics, advanced analytics tools. Now, One thing which I didn't cover in the previous definition and just wanted to put it as a bullet point such that it will be easily understood and conveyed to people is the two-way interaction part. So when I said a real-time data connection, right? So basically I told you need to update the system once the data is flowing through in the physical system. That is good. That is one side flow of data. The other side flow is once your digital twin looks at multiple scenarios and provides you with a solution or provides you with an insight, that insight needs to be implemented in your physical asset. So it is not to just get the insight and just keep it, oh, okay, I'll not do anything with this in the physical asset. No, no. Then it's no longer a digital twin. The information flow should be two-way in for it to be termed as a digital twin. So you collect the data from your physical system, do all kinds of analysis in your virtual replica, and once you identify certain things which can be used to improve the physical system, they need to be implemented in the physical system. This goes with the initial part which you said, like decision making. So whatever decision you are making, that need to be implemented in the physical system. Only then we'll be able to call it a digital twin. One other thing, the entire life cycle integration. So certain times, if you are looking at just the micro scale, like just the daily operation, some decisions made by digital twins might look suboptimal. But if you take the overall bird's eye view and look at the much bigger picture, then it will make much more sense because digital twins, whenever they are making any choices, they look at the entire life cycle of the physical system or physical object. So make sure you have these two also covered when you are doing it. Finally, like some of you have mentioned, this development of digital twins involves a combination of multiple technologies. It will be like IoT devices, artificial intelligence, cloud computing, data analytics, so on and so forth, so on and so forth. It is an extremely multidisciplinary kind of a topic where we need to leverage experience and expertise of a lot of people for it to make a very successful digital twin. Okay, let me see the chat. I see some questions there. Oh, okay, sorry. I think this was not over the question. Okay, sure, no worries. Yeah, so that is basically what digital twin is. So this I covered. So now let's look a little bit about the history of digital twins as such. Digital twins, the initial milestone of it was actually through NASA. NASA actually had to create a replica, not a digital replica, but actual replica of the Apollo satellite, which was having some troubles while re-entering into Earth's atmosphere. So what they had to do was they created a physical replica of this exact satellite and then rather the exact rocket module and then tried to troubleshoot it by using the same parts which are present in the Apollo mission as such. So this was, even though it was not a virtual replica, this was the first time a twin concept was used. And because of how successfully they were able to troubleshoot this, they were able to save the lives of the astronauts while they were re-entering into Earth's atmosphere. Over time, it has become better and more sophisticated. But do remember this, the concept as such has been existing for quite some time. Just that the physical infrastructure available to do this testing has caught up finally with the theory. For example, right, as I've just mentioned, it is a multidisciplinary where it uses IoT devices, AI, so on and so forth. Let's focus on IoT devices. Internet of Things devices in the past used to cost significant amount of money, but over time, the sensors have become more and more affordable. Let's look into the AI part of it. AI computational power in the past used to be much more expensive. It has become much more affordable in the recent past. So a lot more of the advances on the hardware side has helped to make sure the established theory of digital twins is much more viable in practical sense. And once people started looking at the benefits a digital twin gives while implementing it over multiple examples, it has become like a mainstay. And I think I'll argue in the next couple of slides that I personally feel this is no longer future or emerging tech, but rather it's a competitive advantage in the market currently. So it's not even like it come next couple of years, but rather many are using it today. Some of the examples which I wrote here, aircraft manufacturers like Boeing uses it, Airbus uses it. They have one digital twin per aircraft to ensure predictive maintenance. In recent past, a lot of smart cities are being designed using the concept of digital twins, especially trying to make them as sustainable neighborhoods or incorporating more and more renewables into the system. Healthcare is another place where significant progress has been made in adopting digital twins and also getting results out of the healthcare like processes. So it has been expanding significantly in the recent past. Now let me talk about two simple examples to show you the scale of this one, right? Let's say the first one, which is a wind turbine. So I hope everyone know what a wind turbine is. So basically, you have it uses wind to actually generate electricity, and they are very huge infrastructure projects, and they are present in very few places which are very conducive and operate in optimal wind speed. Now, since it's a expensive infrastructure, every particular um, unit present in this has been significantly monitored. So the blades, whichever you see, the three big giant blades, it has so many sensors present on that to collect information on vibration, temperature, wind speed, tensile strength, so on and so forth, so on and so forth, just to ensure it is structurally stable in the operating conditions. Now, once the sensor data is collected, all of this is then sent to a cloud-based digital twin where AI is used to predict which components might fail much before it actually happens. Because of this advanced understanding and kind of predicting the maintenance requirements, the operators are able to work on these particular equipment in the field and make sure they do not have any costly shutdowns. So operators will receive an alert saying like, you need to go and do maintenance on this particular unit, and you have a time span of 3 days before there will be a catastrophic failure. So then they have sufficient time to to arrange the resources, to arrange personnel, to actually go and work on it. Now, this is a very big infrastructure project, right? Let's look it on the other hand, which is personal healthcare. So digital twins have been extensively used to enable in silico simulations. So what do I mean by this? So let's say we are trying to develop a drug addressing a particular disease. So let's say, okay, most of us are familiar with the COVID time, the coronavirus time, wherein the vaccinations were developed at a record pace. Fortunately, scientific community, whom we all should be thankful for, have been working on multiple potential pathways long before COVID came. They were working on different kinds of other viruses, which gave them a jump start to help develop this particular vaccine. Now, these typical drug discovery pathways, how they generally operate is we initially start with 10,000 different possible drug combinations, which will be able to either cure the disease or prevent the disease. From these 10,000 different pathways, based on experience and preliminary results, the lab technicians and the research scientists will decide 10 or 15 different pathways which have the highest success rate to cure the disease or prevent the disease. And they will only focus on these 10 or 15 pathways for full phase 2 development or phase 3 development to make sure it is tested vigorously. Now, this the problem with this one is uh, it kind of out of 10,000 pathways, if you're only picking 10 pathways, maybe with experience you're able to develop it, but you are not in a data driven manner removing the other 9,990 pathways, but rather you're simply saying, with my experience and preliminary analysis, I don't think this will work. Now, digital twins and using in silico simulations, each of this pathway is thoroughly studied before any such assumption is made. So instead of just developing 10 pathways, now we are able to develop all the 10,000 pathways, and each one of it is given an associated probability score of success, and only the high probability pathways are then developed and looked, and rather the capital is invested to develop them further. Similarly, there has been a lot of usage in developing artificial pancreas. The digital twins have been helping scientists to create this in the lab. If they are successful, this will successfully cure the diabetes problem, which a lot of population around the world are suffering from. Same thing has been used to develop heart models for cardiology. So a lot has been going on in the healthcare domain where digital twins are playing a vital role, both in developing cures in the form of drugs and vaccines, but also in helping patient care. So also giving a better experience for the patient to help them while they are recovering from their ailment. I'll skip that one. So some of you actually mentioned this during the word cloud, the word simulation. So this is a very common debate which a lot of people generally have. Like they keep asking, what is the main difference between a digital twin and a traditional simulation? I feel both of them are the same. Can you explain me further? So I have a very simple example. Okay, before I go there, yeah, someone raised their hand. You can ask the question.
Yeah, thank you, Professor. A quick, so the prior slide, when you presented the wind turbine, so just to draw a parallel, we have the weather all around the world. Basically, we collect sensors all around the world and predict what is going to happen, plus minus. Would it also be considered a digital twin wherein I am able to like kind of simulate what direction a cyclone takes, etc.?
So as you said, within within your full sentence, you use the word simulate a lot. Simulation definitely yes, as long as they are trying to address a decision-making problem, then it will fall in the realm of digital twins. But otherwise, it will be a simple simulation, and that's what I'm trying to explain in this particular slide. So okay, so maybe I think I can connect that into this one. So let me explain this one, right? I would say a simulation versus a digital twin, right? Consider a age-old atlas map. Let's say we are traveling like a tourist to a new city. We go to the city information center and ask for a map. We take a paper map. I think many of you, if you are traveling, you'll be very familiar with it. There'll be a paper map of the entire city, spots to look at, spots which will be nice to look at, nice to eat, so on and so forth, so on and so forth. This traditional paper map provides you a snapshot in time showing the entire terrain. Basically, whenever the map was printed, it basically tells you, okay, this is how the terrain is, this is the direction, this is the streets, how you can go from point A to point B. If you want to walk, how you can go. This will also have the static data in the form like roads are present from how to go from place A to place B. Now, let's say compare that with the navigation system which is present in the vehicles these days. So it uses the traditional map, and on top of that, it updates that map based on live feedback. So if there is a road closure happening in one particular section, then it automatically reroutes us into a different road, into a different pathway. It will also be our active partner in achieving the objective of moving from destination A to destination B, either the shortest time possible, or the most comfort way possible, or the most sheltered way possible. For example, if you're walking in a city, some might prefer to walk on flat surfaces because they do not want to go up and down the hill because either of their age or any personal ailments. So in that case, a traditional map will basically be useless. Whereas in a dynamic navigation system, you can add in these constraints, and then the map will map it exactly to your needs. Same thing for the traffic. Let's say Google Maps, right? Google Maps uses this very widely, wherein like if I'm opening the Google Map app on that particular street to go into a direction, if at the same time in the same street 10 different people open it, then Google assumes that there is significant amount of traffic present on that particular road. And based on the traffic, it suggests you alternate routes. Uh, Obviously, there'll be a downside, like everyone need to use the maps, Google Maps as such, but it solves a bigger purpose of going from point A to point B in the most optimal way, fitting to your necessities. That is more compared to a digital twin. So I think I hope this clears the question which many of you might have on like what is a simulation versus a digital twin. Now on the question which was asked, I have been I know that weather updates, tracking the temperature, rather the wind flow, cyclone movements is extensively used in multiple applications. I, for one, know that in maritime, it is used significantly to plot better routes. It also is used to ensure they avoid any turbulent weather such that they reach from destination A to destination B. That, in a sense, is a digital twin, wherein you are actively changing the route of your vessel to follow the path of least resistance based on the information whichever you are getting from these satellite images of how the atmospheric conditions are being changed. Now, on the other hand, if I'm just using this particular information of wind movement or cyclone movement just for understanding and not taking any decisions out of it, then I would refrain from calling it a digital twin. As long as we are using this information to help us solve a problem, to help us in making decisions, then yes, it is a digital twin. I hope that answers the question.
Yes. So just now it things where I have control, I can change parameters would be a digital twin. In a cyclone, I cannot change anything. I just can observe it. It'll be a simulation.
Exactly. The idea is using that information, can you actually do something about it or not? If not, then it's good to have that information, but it is uncontrollable, right? So now, why do I say this one, right? At the end of the day, what we are trying to solve, the core problem here is, why are we developing all of this, right? We are trying to develop this to say, can this help me to solve a real life problem? Or can this help me in doing this process in an efficient manner? But then someone comes to you and tells like, oh, this is the entire information, but unfortunately, you can do nothing about it. Then the main question comes at like, okay, if I can't do anything about it, is this information even useful for me? Or rather, if I can't do anything about it, what can I do about it, right? So idea of a digital twin is you need to be able to influence the decisions, and that is where the cornerstone message of digital twin is.
Got
Okay, now let's move further. So now I have talked about the definition of a digital twin, different examples. It's okay. We talked about the distinction between a simulation and a digital twin. All of this is fine. But the question you need to ask, especially from business perspective, is, so what? So why do digital twins matter to me? Now, to answer that question is why I have this on the next slide. So what's happening? I think I covered some of it in our previous slides, which I said that these days, computational power is becoming more and more affordable. At the same time, a lot more sensors are being deployed in the field in multiple domains. You can have it in production lines, you can have it in logistics, you can have it in traffic signals, you can have it in healthcare, so on and so forth. For example, in healthcare, almost a significant chunk of people are monitoring their health through the help of personalized devices like smart watches. Some of them are regularly doing taking the help of their phone to keep track of their exercises, so on and so forth. So a lot more data is being generated. Now, once you have better data, the next obvious question would be, how do I make most use of this information? And digital twins is one of that particular thing. So system complexity has been growing a lot, and data availability is also growing a lot. At the same time, the hardware side of it is becoming much and much more affordable, not just sensors, but also computational side of things. McKinsey predicts just this digital twins as a market is growing about 60% CAGR on annual growth. It will be a $73 billion market by 2027. That is by next year. So it is a sizable market value. And I think Gartner has named it as an emerging technology already in 2017, but I would say it is no longer emerging, but rather a competitive advantage today. That's what I would like to say here. You can see a lot of examples already being used. So Boeing basically uses one-to-one digital twin for every single aircraft they manufacture. So every single aircraft has this logged out based on which direction it is going, where it is going, to help the operators do predictive maintenance on these equipment. And because of this, it saves nearly 30% in maintenance costs. Now, since Boeing was doing this thing, Airbus was forced to do this also to help with their predictive maintenance. So in a way, if one of your competitors is doing it already, you will be forced into a corner because of the benefits digital twins offer. Autonomous driving is another place where digital twins are used very, very widely. And Tesla is one of the pioneer in this particular part, wherein Tesla uses digital twins to basically, whenever they are doing any kind of a software update or software push, they first run it in a digital twin, ensure it is smoothly going through, and only then push the patch over to the multiple devices present around the world. Close to home, I'm based in Singapore, so close to home. Singapore has this Smart Nation initiative, wherein you basically the entirety of Singapore, the entire island city state, is like a replica of this, a 3D replica of this entire country has been created, especially the residential places and the office spaces. And each of the building has their energy measurements, the people presence, what kind of a building material is used, what is it architecturally present, what is the orientation, so on and so forth, so on and so forth. All of this is present as a digital replica. Now, what is the use case based on this? What they're currently doing is using this information. They are creating sustainable neighborhoods around Singapore. So when they are redeveloping an existing neighborhood, they are developing it in a fashion to solve some of their objectives. One of the objectives is the elderly population in Singapore is growing a lot. So they are developing neighborhoods which are much more adult friendly, in the sense you have a lot more ramps, you have a lot more shuttle buses, you have a lot more public transport, have a lot more restaurants, or rather the small coffee shops kind of a place where people can hang out. And to make sure people are actively working out at that age, because that's an age which is highly susceptible for physical ailments, they are also doing regular health-based programs in these particular neighborhoods to get the adult population more and more active, the elderly population more and more active, to prevent diseases. And as I said, the initial reason for creating a digital replica might be a different one, but once they had this replica, they made it into a digital twin with different objectives. For each objective, you can design the neighborhood in that particular direction. And all of this is only possible because you have a digital twin. You can pivot in whichever objective function you want to do it, but if you do not have it in the first place, it will be much more difficult. So as per me, I would say digital twins is no longer a future tech. I wouldn't say it is emerging at all. It is today's competitive advantage. If you have it, if you know it, if you are able to implement it, people in your field, in your competition in your field, will be forced to adopt to it, because the benefits which digital twins offer are quite a lot. Someone raised their hand. Yeah, one by one. Maybe Deepak first and then Atif.
Hello, sir. Thank you. All this content is fascinating. So, just a quick question on the second example you used on this. Tesla, you said uses car digital twins to improve software updates. So, are you saying that Tesla has a digital twin of every car that they sell? And that is, if they do, then is it efficient that way, or does like
Okay.
every car company?
Tesla does not have, yeah. They do not have every single car, but they have for the model. For example, there are multiple models within Tesla. They actually have the mod for per model, they have a digital twin. Unlike Boeing, Boeing has a one-to-one digital twin. Tesla does not. Tesla basically has, okay, I have 10 different models. For each model, I'll have a different digital twin. And then they also have something like different variants, right? So what happens is, cars are subject to usage, and more often than not, mileage will have an impact on it. So if you are having 100,000 kilometers run on a car, it will be slightly different, especially the wear and tear side of things. So they also have different models based on the progression of a model, but not one-to-one. So they do not do one-to-one.
Got it. Okay. Thank you.
Atif, you can go for it.
Yes, I don't have a technical background as deep as others maybe, but just a fundamental question. One of the things that you mentioned in one of your, the first step is virtual representation, right? You talked about healthcare examples, you talked about Boeing, and these are industries where safety can be there's a very small margin on safety. So I'm trying to visualize that virtual representation cannot account for, it's not a perfect representation, I take it, because human organs are very complicated. So how do you compensate for imperfect model when the whole system is running in real time?
Very, very valid point, Atif, and thanks for bringing it up. So let me address it. I'll not go into technical side of it, but let me address it as a whole, right? So, okay, as I said in one of my initial slides, like I have a PhD in optimization, right? So in our lab, we used to have a poster because I was like working in that field. We used to have a poster which said that 100% of the models developed are wrong, but some are useful. So this is the motto whenever we develop digital twins. The idea here being there is nothing like a perfect model. You can never replicate entirety of it in a digital version. You try to make it as close to the real thing as possible, but you cannot make it 100% anytime. So what do? We then start looking at what are the trade-offs which we will get. Let's say, is it okay to have a model 90% accurate? Let's say if I'm talking about traffic simulation, like vehicle traffic simulation on roads. If I'm getting a model about 90% accurate, then I'll be like, okay, worst case scenario, what will happen in this case is people will have 1 more minute spent on traffic compared to 0 minutes spent in traffic. If that is the margins, then I'm much more happy to even have a 90% model. Now, let's say on the other hand, if I'm looking at Boeing aircraft, right? In this case, am I okay with having a 99% model or am I okay with having 95% model? Because having the added accuracy increases the cost of development of the model. So if my business case does not support basically the bottom line, the dollar value, does not support me investing additional money to increase that accuracy, then I have no motivation to do it. In Boeing case, the dollar economics actually support it. The dollar economics being the cost of an aircraft is extremely high. So for them to have that even 99% accuracy helps them to save a lot more money. And it is like once you have this something we call as institutional memory, right? So you develop one digital twin. The first time you're developing it must have been extremely difficult. But if they're same model and make, the accuracies keeps increasing over time because you'll be adding more and more features into your existing digital twin. So depending on case, and obviously the dollar economics matter a lot. And based on that, you decide what is the accuracy you are okay with. Some you will not be okay with, where you have to make a trade-off. Some you might get by because, yeah, even if I'm able to replicate a system 90%, I might be able to save significant amount of money. We also have something, probably many of you might be aware of this thing, called as a Pareto solution. So basically it says that if you address, if I'm not wrong, hopefully I cover this thing. If you address 20% of the problems, you might be having 80% of the savings or something like that. So if I get 80-20 rule or something like that, it's basically trying to say that the lowest hanging fruits typically give you a significant amount of savings. And that can also work with simpler models. Yeah, hope that answers the question.
Yes, it does. But I understand you talked about Boeing as an example. Would a similar, I think the analysis would be a little bit different in case of healthcare, correct?
Yes. Healthcare is much more complex for a couple of reasons. One, obviously, is the safety side of things. Second is the privacy, data privacy side of things, ethics and data privacy side of things. So that side of like using patient data is a little more lagging. But when it comes to drug discovery and drug development, that is much more better to use digital twins because one, it does not involve the level of data privacy regulations because no patient is involved while the drug is being developed still. Early stages is when I'm talking about the treatment pathways. Their patients are not yet involved. They will only come in like phase 3 trials or phase 4 trials. So in those places, digital twins actually help you fasten things significantly and have a good savings, while you can also have a lot more margin there. So if you are trying to figure out a model, even if your model is 95% accurate, if you are able to get a quantitative measure of telling which particular treatment pathways are more viable than the others, I'll take it any day. And then when I'm doing it in real life, if I realize the model was not fully capturing certain nuances, I will help to train the model for future studies. But at least it will be acting like a very good filter for me to move into and help me identify the viable pathways. That's how I would see it.
Thank you, sir.
Someone else raised their hand, sorry, but I can't see who it was. Okay, let me see. Okay. So yeah, dollar is important, but risk liability may be the variable to justify additional cost to achieve higher accuracy. Yes, that's a very valid point, Jeff. And at the end of the day, we cannot put a dollar value on people's lives. Thus, that particular where it's actively involving people is a little more trickier. People's life is a little more trickier. Let me give you a caveat on this one, right? So there is a good thing and a bad thing about AI and digital twins in this realm, right? So this happened in San Francisco, I think, a couple of years back. San Francisco is one of the places where you actually get to see autonomous vehicles, especially in the form of taxis or kind of cars roaming around the streets. And typically in San Francisco, in a day, there'll be roughly about 20 to 25 accidents involving people, just humans. Whenever they are driving, 20 to 25 accidents happening per day. They never were even mentioned in either internet or in newspapers. But there was one accident which involved autonomous vehicles. That particular accident was in the limelight for close to 3 months. Now, the question here is, if you're talking purely from the perspective of human life, weren't the other 20 or 30 cases which were involving accidents every single day as worthy as it? Or is it undue question mark raised on the AI? This was one of the questions. Then people, after looking to multiple things and talking to multiple people, identified the core problem of the entire conundrum. The conundrum here being, if in the case of an accident involving people, you know whom to blame. The accountability was always person A or person B. So people were a little more comfortable with that. Compared to when it's an autonomous vehicle driving, whom do you actually put the accountability on? Because the people in the car are not accountable because they are not driving. The other car person, do you say that it was a problem of the other side of the person, or do you blame the person who actually created this algorithm in the first place? So because of this accountability problem, that entire autonomous vehicle debacle happened during that time. Now, why am I saying this thing, right? Digital twins does everything at scale. So you'll be taking decisions at scale, influencing a lot more. The process as such will be influenced significantly through digital twins. So if you are developing one, you need to be fully aware of it from day one to ensure you do not let biases to come into picture, because they will be aggravated significantly at scale. Same thing, making sure that proper ethics, data security, and privacy are followed from day one. That is essential when you are developing your digital twins, because someday in the future, some mishap might happen where you need to properly defend your viewpoint, saying that this is the reason why it is being done this way. People may argue, but as long as you have a logical reasoning for why you are doing what you are doing, you will basically be covering it. Like, you'll be covering yourself from any potential liabilities. So just wanted to go in that tangent to help you people understand this concept as such. Hopefully that answers that. Okay. So yeah, okay. Now, before we move into the second part of today's session, which will be focusing much more on digital twin architecture and what are the various components present in that, so on and so forth, so on and so forth. Let's take a 10-minute break now. Yeah, let's come back in 10 minutes. Then we will look at much more details about digital twin as such. In the meanwhile, if you have any questions, feel free to ask, or you can also type in the chat. Okay, see you back in 10 minutes. maybe in an hour's time. That will be the last part which we do in the session. So in case, in the meanwhile, try to find it if you are not aware of it. Do ask your colleagues to help you with where the location where the file is actually present. Yeah, make sure that you have it downloaded onto your computer and you'll be able to open it on your computer. Okay.
So, sorry, sir, I just missed what you said. I'm sorry.
Yeah, so there'll be at the last part of today's session, we will be doing a simulation. For as part of that, I have already uploaded the HTML file which will be required to run that particular simulation on your local computers. It's not a heavy one; it's just like a website. You open the website and that. So yeah, it should be present in the resources tab in your what do you call the CRM platform, the platform where you can see all the courses. Please download it for the later part of today's presentation. So yeah, let's get started on the other part of it, right? So until now, I talked about we using a lot of technologies, we using a lot of different things, using IoT, using simulation, AI, so on and so forth, right? Let's actually segment whatever I have mentioned into different layers to help us understand, to have a structure to the entire digital twins process. So okay, before that, I see someone message something in the chat. Let me check there. Yeah, that's the file. That's the file. Yeah. So now let's try to segment it into different layers and try to understand the different nuances present in each one of these layers, such that we'll at least know on the surface level what these are. Being upfront about this, I typically take As I said, 14 weeks to cover the entire digital twins course. And this particular digital twin architecture portion is like for each topic, we spend a week or 2 weeks in the case of simulation, actually. So that basically like 4 hours of lecture for each layer. Obviously, we do not have so much time in today's session. So I will try to cover all the basics such that, okay, again, it all goes back to what was my motivation and what was I expecting you people to learn, take out from this session, right? My motivation fully is to equip you people with sufficient knowledge such that in future, when someone talks about digital twins, you will be able to ask the right questions. You'll be not lost because they are using different jargons, but you'll be able to understand what is happening and actually have an intelligent conversation with the person. That is my motivation for this entire session. Obviously, I have prepared slides for each one of these layers. The entire slide deck will be circulated to the class after today's session. So you can actually go into deeper details if you want to understand better. And I'll also share my LinkedIn contact at the end, wherein we can keep in touch in future if you want to go deeper into this particular topic or leverage into this into any of your examples. I'm happy to collaborate on this one. Okay. So let's start. Okay, Jansi Rani, I think you raised your hand. Please go for it.
I just want to know, because you mentioned about you have this 18 weeks of course on this digital twin. Is it also planned with our program, or is it some external course you are referring?
Oh, no, it's what I teach in the local university in Singapore.
Okay. Understood. Yeah. Thank you.
So yeah, let's start. The entire picture which you see on the right hand side of the presentation, that's what we'll be focusing in the next maybe 20 to 30 minutes. Again, just being upfront, all the pictures whichever I have used in this particular presentation were developed using LLMs. All I did was give it a good prompt and obviously give it sufficient information for each one of it, but developed using LLMs. So if you want to reuse it, feel free to do that. So let's start it. Before going into each layer, I want you people to focus on the arrows. You see the gray arrows going from bottom to top and the red arrows coming from top to bottom. So when the gray arrow is going from the bottommost layer to the topmost layer, what is happening is the raw information whichever is being collected, it is being processed and it is being refined to get actionable insights over different layers. We'll talk a little bit deeper in that. On the other hand, the red arrow whichever is coming down, that is the feedback received by the decision maker, which the decision maker actually took and is flowing down the system to implement that feedback onto the physical system as such. That's the difference between these two arrows. Now let's start with the bottommost layer, which is the physical system or the real world systems. This can be anything like a construction area. It can be people. It can be machines. It can be equipment, environmental, or anything in that realm. So any kind of a real life system, whichever we want to create a digital twin, will all fall in this particular layer. Now, let's say I'm trying to develop a healthcare digital twin, or if I'm trying to develop a digital twin to replicate diabetes solution or replicate logistics for Amazon or replicate maritime ship movement. All of this will fall under the physical or real systems in this hierarchy. Now, that is one of the key constraints for creating a digital twin, right? Which I said, like, you need to have existing physical object or system. You people might ask the question, so do you actually mean that all of these will be only implemented for brownfield projects or like existing infrastructure, or can it also be done for a greenfield project? Because what happens in a greenfield, you will not have the physical system already established. You're actually going to construct in that particular site from scratch or re-establish from scratch. What I mean by having a physical asset or system already in the real world is you need to be aware of what kind of outputs you will get from the system. So even in a greenfield kind of a project, you would have existing precedents, which is systems which are already running in different locations, from which you can gain the wisdom and from which you can gain the data, how it is being processed, so on and so forth. So as long as this new system, whichever you are developing, has a precedent present in the world, then you can use digital twin even for that. Now, once we have the real world asset, then comes the data acquisition. What do I mean by this? For any sort of models to function, data is going to be essential. Now, let's start with a very simple, extremely basic example. Almost all of us are familiar with air conditioning. So let's say I want to measure a temperature of the room and accordingly increase or decrease my air con settings. Very simple problem, right? Now, let me pose you the conundrums even for this. When I say I need to measure the temperature, what kind of temperature sensor am I looking at? Am I looking at a temperature sensor which is cheap, extremely cheap, and which might be giving you data every second? Or should I be looking at extremely expensive sensors, which might also be giving data at a microsecond, nanosecond kind of a range? Or should I go somewhere in between? Now, apart from this, should I just install one sensor? Should I install multiple sensors in this particular room? Or should I have, let's say, a combination in these multiple sensors? So I have one expensive sensor, 10 cheap sensors installed in the room. Or next conundrum is, where do I place these sensors? Should I place the sensor at every corner in the room of the floor? Or should I place the sensors on every corner on the roof? Or should I hang one sensor at the center of the room, like hanging in the air? Where should I actually do the measurement for this temperature? See, the question was very simple, which is measure the temperature of the room. Within that, there are so many conundrums. Now, I forgot to mention one other thing. Let's say I have multiple sensors. Which sensor do I believe if there is a conflict? So all of these questions will be addressed in the data acquisition layer. Now, you can ask me the question like, okay, how do we actually address this? So to address these questions, that is when we will be using the experience of people in this field, right? Something is like, if you have a budgetary constraint, then you actually say, okay, my budget allows for so much amount of sensors. Let's say I can only afford extremely cheap IoT sensors. I cannot go expensive ones. So you have your options cut out because of the constraints placed on you. Or you realize that you already have an existing high-end temperature sensor. You're basically reusing it. You're getting it from another department and reusing in your case. So in which case your problem is solved. If not, then you start realizing, okay, how do I actually merge the data coming from multiple data sources, measuring the exact same thing? Every sensor is measuring the temperature in the room. And let's, for example, think everything is placed side by side. Even then, if there's a discrepancy on one sensor to other sensor, how do I identify? In those cases, you kind of rely on the accuracy of the equipment. So typically, and more often than not, the expensive the equipment is, the more reliability and accuracy it generally has. Compared to a cheap 10 cent, rather 5 cent IoT sensor, you expect a $20 temperature sensor to be more accurate. And you establish this hierarchy in the data acquisition layer itself, based on what you are going to measure. Once you establish all of these rules in the data acquisition layer, the data is collected. Now, the data is collected, well and good. How do I actually move the data from the sensor into the location whichever I want it to be in? Then you have the question like connectivity. How do I connect my sensors such that they will be passing me the data for further modifications, further analysis? You have options like either use the Wi-Fi network, or use Bluetooth network, or use the 5G, or the age-old, just connect a hard wire to the sensor, download the data onto an equipment from there, or onto your computer from there. Now, each one of this has its own pros and cons. For example, if you are talking about using cheap IoT sensors, typically these sensors are going to be extremely energy efficient and they will be of low energy consumption. If they are of low energy consumption, they will not be able to support a 5G network, because connecting to a 5G network to pass your data is more energy intensive than just passing it through Bluetooth. So based on the budget, whichever you're allocated, you will also be constrained to select which particular combination you need to do. So probably you'll decide, like, there are so many sensors. So I'll probably use a Bluetooth network or a Zigbee network, where all the data in the sensors are just conveyed to each other via Bluetooth. And then I will have a computer or a desktop placed in the same room, which will collect all these Bluetooth information. And from there, using either wired internet or Wi-Fi, I will push the information into cloud or any other location where I want to save it. Now look at this. Just within 2 layers, we have introduced so many amount of permutations and combinations. The idea here being, you can have a combination saying like some amount of your sensors are following through Wi-Fi, some might be following a Bluetooth network or a Zigbee network, some might be pushing data using a 5G network, and some are extremely traditional and wherein you connect a wire and then collect the data. For each one of this, you have to have different protocols to ensure the data flows seamlessly from the place where it is collected all the way to the place where you want to process it. Now, I have my data collected and pushed. Now, where do I store this data? There are again options for this. You can store the data in the local place itself, in the place where the data is being collected, have a server there, store the data there, or push all the data into cloud storage and doing cloud computing, or a hybrid combination. Now, let me give you a very practical example, right? So for a second, let's think we are riding in an autonomous car. Autonomous car is flowing through this, rather is driving through the streets of Singapore, happily going through. Then you suddenly start realizing, hey, I have this problem, which Prof mentioned in one of the class. How is this processing the data and where is it saving? Then you start thinking, so I am driving, rather the autonomous vehicle is driving, I'm sitting in it. It is observing the traffic over multiple locations and taking decisions. If each of this data collected for every single layer, rather every single second or microsecond, if it is going to be pushed into cloud, and if the car is going to wait until it gets signal from the cloud, then your car will not even be driven, because there will be latency always present. So in those cases, you expect entire processing, at least for the navigation side of things, to be happening within the car itself. So you collect the information, process the information, get the insights and actions in the car itself for an autonomous vehicle. Now compare that to, let's say, what is my preferred music when I want to travel in the morning? Or what is the aircon temperature which I want to set up, or preheat or pre-cool my car before I start the journey? These kind of decisions, they are not so life and death. So they need not be computed on the edge. They can be computed on the cloud. Now, you can ask me the question saying like, hey, Prof, why not have everything on the edge itself? Because you can get the information done, processed very quickly. The idea here is, it is always going to be a trade-off between how much amount of infrastructure you can have and the latency. So you can have the best latency if you have all the models, computation, storage, everything happening at the edge. But it is extremely expensive and it does not scale. What do I mean by scale, right? So today, let's say you are having necessity of X amount of processing power. Then you start realizing, oh, instead of X, I probably want 2 times X. If it's an edge device, you basically need to either have additional slots, get additional equipment bought and installed in each and every single location where you're expecting this change. Expensive affair, and also quite some operational intensive. Now, on the other hand, let's say you have a cloud computing system which is already set up. So there, adding and removing infrastructure is much more economical and can be done scale. So if you realize that you're only using this equipment on Thursdays, on remaining days, you can use the equipment for some other use case, so on and so forth. Thus, the trade-off will always be between what is the acceptable latency which you can afford versus the cost or capital which you can spend for this infrastructure. Now, once you decided this, that's when you move into the brain of this entire digital twin, which is where the modeling and simulation happens. What do I mean by this? So you are collecting the data and you are trying to get actionable insights from this particular data. So the idea is, using this information, you develop, let's say, a forecasting model, or let's say a recurrent neural network model, or a deep learning model, so on and so forth, so on and so forth. Each of these models will be actually set up in this layer. So it can be a physics-based model, purely following equations, or it can be purely data-driven models, where even though you are not aware of the underlying equations present, just because you have a lot of data, you will be able to predict what the outcome will be for a particular input. That is a data-driven model. And then there will be combinations wherein it's a hybrid kind of a thing, where some parts can be created using equations, whereas some parts you have to rely on data to develop the models. So this particular layer, whichever I'm talking, is where we spend about 2 weeks going into detail about each and every model. I will take some time and show you the different models as such, but we will not be going into details, like in-depth details about this. Now, finally, we have painstakingly developed, distributed, had sensors installed, data collected, data computed, processed, and using our very, very cutting edge model, we came up with good actionable insights. All of this will be for naught if the stakeholder, the final person who will be taking the call, will not be able to understand the outputs. That is why the interfacing, the dashboards, and the application layer is the critical piece for the entire decision making in a digital twin to follow, because you are going to explain a complex process in very, very simple terms for your stakeholder to understand, because stakeholders might not have as much time to understand in-depth models, but they might be the people who, with their experience and expertise in that entire domain, will be able to take the calls very, very quickly. So you need to ensure your entire digital twin is going to simplify their interactions. So you need to create charts in a way which is comfortable for them. You need to create alerts in such a fashion that they are able to act upon it on the fly. You need to also ensure decision systems are set up in such a fashion where it is not too difficult for the stakeholder to enforce a particular decision, whichever they take. Why is this the most important piece? Because the cornerstone of a digital twin is decision making. And typically, the decision making, the bottleneck will be the human, the final stakeholder. And making it as smooth and as easy for them to comprehend this complex topic will go a long, long way in defining the success of the digital twin. So people should spend a lot of time in developing successful and good dashboards, and also provide good alerts for the stakeholder to understand and act upon. Any questions till this point? I don't see anything in the chat. Are there any questions on this? Go for it, Chandrasekhar.
Professor, there is a for a comprehensive decision making. There'll also be data required from multiple other sources. Where will those data feed into? Will it directly feed into the computation layer? For example, in the case of windmill, you may need a weather forecast of that place, right? So will it feed in this diagram? Where will that feed in, and how does that work?
So if you're talking about the because we are looking at the entire decision making, right? So what I would say, if there are auxiliary places from which you are getting the information, they should actually feed into either the data acquisition layer or into the computational layer. So let's say you already have established systems, you have no control on it, you're just taking the information from it, then they directly feed into your computational layer. Or if you have a say on what kind of sensors are going to measure it, then they feed into the data acquisition layer. That's how I would say it.
Got it, sir.
Yeah.
There's another follow-up question, sir. On the last layer that you also have human in there, right? So
Yeah.
the human there is the human in a typical framework. Is human feeding in data as well and being considered as a system here, or is human in the loop for the final decision making?
So when I talk in the human, the physical and real world systems, right, they are basically like a system. For example, human resources want to understand what the drop-off rate or resignation rate of humans are going to be in that particular wing. Or you can also have like, what is the behavior of people who are cycling or who are driving? So those all will be part of the systems which we are trying to model using the digital twin. Now, apart from that, each and every digital twin, at least as of date, will have human in the loop.
Okay.
The reason is very simple on this one, right? When we are trying to introduce new technologies or much more like rather, I still remember, sorry for going on a tangent on this one. I still remember in early 2000s, most of the job descriptions used to have a line item saying that we require the candidate to be familiar with the Office suite. So basically, they were expecting everyone to know Microsoft Word, PowerPoint, Excel, so on and so forth, so on and so forth. These days, people are no longer asking that. Reason being, everyone is familiar with this technology and they are expected to know it. So when you're talking about digital twin, in the initial days, the same thing happens, wherein like you have to kind of spoon feed everything and you have a human in the loop to double verify whatever decision is being done. Over time, as they achieve maturity, then slowly and steadily, the entire process can be automated by itself. Where in most places, you can have the digital twin itself creating the final decision and conveying to the people who it needs to convey, while only involving the human in extremely critical activities. At least that is how I envisage the entire ecosystem evolving over time. But for now, human is the major piece in the decision making still. Like your digital twin does everything, still need to be signed off by a human. This goes directly to what I mentioned sometime back regarding the accountability part of it. Currently, if something goes wrong, we don't know who is the person accountable for it. If it is fully done by a digital twin, then is it going to be the person who developed the software? Surely not, right? So for now, still, you are going to have a human in loop, but with much, much higher efficiencies while they are doing with this, or rather, while they're operating this one. Now, someone can actually ask me the question, higher efficiency is well and good. At the same time, higher efficiency means these people will be taking accountability to a lot more projects than they were initially taking. Will there be this accountability headache coming on one person? And one person will be accountable for 100 projects instead of just being 2 or 3 projects in the past. In which case, you will not be able to fully focus and fully be able to ensure all the checks and balances are fully done. But that's a question for a different, more governance side of it. But good to have that in mind too.
Sir, if I may ask just one more question here.
Go for it.
Yeah. Sir, when let's say in case of Tesla and the example you gave of an accident, right? And then there are, and if it happens, typically in this case, when it is humans and there is an accident, the legal liability is on the human being. In these scenarios, how does it work from a liability standpoint, insurance standpoint, kind of a situation, from a business model standpoint?
So that is the biggest conundrum for implementation of any of these AI systems around the world currently. So what happens, at least till recent days, in the case of the one which I was mentioning in San Francisco, the company which was operating that actually took the liability for it, and they paid and settled it.
Got it.
But going forward, that is because that is not a sustainable pathway, right? Because every company at the end of the day will be having their own bottom line or P&L statements which they need to follow through. If they are keep on, and in some cases, especially when you mentioned the insurance side of things, right? Luckily, since these AI systems have everything documented very, very well, the data is extremely robust in that sense of it. People are able to actually pinpoint the blame even better compared to the previous scenarios. But you can always argue in a court of law saying that the machine doesn't know, because people still think it is like a black box where they don't know what is happening in that. Still, people are skeptical about it. But over time, people will start believing and trusting these AI systems much more to ensure, even in the court of law, people do not, like, there's always a saying, right? You assume someone is innocent until guilty. In AI cases, more often than not, what's happening is it's assumed that AI is guilty before innocent. So at least that will change, and that's what I foresee the future happening.
Thank you, sir.
Okay. Yeah. Nimesh, you can ask the question. Go for it.
Yeah, Prof. So I have been working on trying to basically understand the application of digital twin in agriculture, So just to improve the logistics and all those things that are there and reduce the load of the farmers. But it has, like, as you mentioned earlier, that digital twin is no more an emerging tech, but it has not found such nice grounds when it comes to agriculture. So would you call that it is not advisable to move forward trying to do digital twin for agriculture, or do you think it is an emerging tech for agriculture as an industry? What is your view on that?
Yeah, thanks for pointing it out. So as I said, I had a couple of students in the last year who were actually working on something similar to this one, where they were using a digital twin to improve the yield of farms. One was from rural India and one was from rural China, where they were focusing on different use cases. So I wouldn't say it is an emerging tech for agriculture. It is being used by people. I have seen examples in that, especially, okay, it is all about dollar economics at the end of the day, you see. So if the particular village, entirety of the village, if they are all willing to do this, then you will have sufficient money to actually build the system. Unlike if you're having just 1 acre of farm who wants to do this thing, in which case it will be much more capital intensive. So typically you bring in multiple people onto this, because scalability is not a big problem for digital twin. It is a lot of upfront capital expenditure which is going to be there compared to the incremental operating costs. So as long as you are able to make a business case, it is not an emerging tech. It's the problem is here. Problem is not with the technology or side of things, but rather dollar side of things. So yeah, tech side, no problem. You need to just make a business case for it.
Okay, just an add-on to that. So, okay, I understand the size of the farms in this part of the world are smaller, but that's not the case with the farms that you see in the US.
Yes.
But when I was doing the research, we could not see the application of digital twin in that part of the world as well. They have done a lot of innovations in terms of farming, equipment and things like that. John Deere has done a lot of research and they're trying a lot of things, but we don't see any like real concrete evidence where this is being implemented. So do you feel that even the dollar economics doesn't work even with the scale of the farms? Maybe if you have more information,
yeah,
if you can
so
enlighten us.
Yeah, so what I have personally seen, again, agriculture is a little far off from the field of expertise which I personally have, which is in the healthcare side of things. But I can tell because I had students who were working on it. So apparently, a lot of this has been in development in certain parts in China. But I also heard some places within India who are actually developing this, or rather using this. I think there was a session in the morning. Someone was mentioning that I think in India, Andhra Pradesh, I think, yeah, Andhra Pradesh was using digital twins for something to do with their land pooling or something on that. So probably those will be the use cases which you can start looking for. But probably I need to look for more before I send. Maybe I can send it to you after I do some research on that myself.
Yeah, that's very generous of you. Thank you very much.
Yeah.
Thank you.
Prince, you can ask the question. Go for it.
Yeah, thank you, sir. Well, just I'm having a view around this, the financial world, and aligning it with the tech. But the digital twin, still I'm not able to, conclude it where exactly in the financial world, specifically in the corporate investment banking, right? I want to see whether we have a specific, bank or any other big giant are using it. Because I see they are using AI models, they are using ML, AI ML. They have a very good infrastructure which generates the insight. But how digital twin you think can be implemented or being implemented by some other organizations into finance?
Yeah. So finance world is one thing wherein the world as such is extremely good from the simulation and analytics perspective. So they have a lot of analytics happening for, let's say, any kind of an investment, any kind of influence, such that the returns are as much as possible. So at the end of the day, it's all about going to be the dollar value, so on and so forth. And probably investing in digital funds might be a too hectic kind of a thing. But I personally know they do this for the customer interface places. Not sure about the corporate banking as such, but consumer banking, right? In consumer banking, especially for the AI chatbots are present these days, right? A lot of them have been vetted very thoroughly in the digital twins before they are actually released to the public. So that's a space where there is some potential for digital twins. But otherwise, digital financial sector is already an extremely well analyzed sector, if I would say. So the depths and the insight which you get adding another technology will be very, very minuscule compared to the leaps and bounds which some other sectors will have.
Okay, and one more thing, because as we all agree on the point that market is quite sensitive, right? In case of any speculation comes, so on the basis of any statement, for example, if Elon Musk gives any statement on anything, right? Then the market reacts very in a very quick succession. So in that case, there is a lot of unstructured data generates, right? Because that unstructured data is very difficult to analyze because until it is into a structured form. So I think a couple of weeks back, I was discussing the same thing with some of the colleagues into my organization, and that's where I thought a kind of pipeline, a kind of infrastructure be in place which allow me to structure this data on a real-time basis and allow me to get the insight out of it very quickly, so that I can manage my funds, which may take a dip into a maybe in a couple of hours. So do you think such kind of area is also where I can at least, not 100%, but at least some part of the digital thing can I implement it?
So yeah, so the one which you are emphasizing is much more in the data acquisition side of things. So what happens here is you're basically I would say you are trying to do a part of it, and since let's say like what you mentioned, right? Elon Musk is making one statement, the market reacts extremely quick to this one. So it's like then you kind of where like it's like you have to kind of predict what will happen even before Elon Musk makes a statement. So probably you'll be doing much more like a simulation kind of things where like person A gives very weird statement. What will be the impact on the market? So it'll be much more of a simulation domain than a digital twin domain. That's what I would say. Because you'll have like set number of scenarios which you want to test. If you want to stretch it to digital twin, the tricky nature comes wherein like you kind of need to do it live, but the market itself reacts very, very quickly to that. So I'm struggling to think like where else it will be of value apart from that being like another replica of it. You might do some other cases, but especially the money terms, I think market is extremely quick in representing all of it. So I don't think a digital twin will be able to be fully utilized in that scenario, unfortunately.
Yes, indeed. I think even I thought the same. Thank you for the explanation.
Yeah.
Thank you, sir.
Yeah. Okay. Any other questions? Okay. So just let me, I will not go into details, but just let me show how the other parts in the slides are organized, right? So the data acquisition layer, I'll have some information on this thing. I also have something on data fusion, so on and so forth, bringing in the examples of autonomous vehicles and trying to answer the questions, right? Similarly, each one of these sections, I'll be providing some information. So let me show what I was talking about, the models as such. So see, in the modeling section, physics-based models can be basically lumped into 10 different groups. We typically spend some time in each one of this model to understand it better. But again, you people need not understand that level. But think of it this way, like your entire modeling based on physics are just 10 different models. That's it. Each one will be having slight different variations, but just in the step. So if someone basically asks you in future, or what is your model based on, you'll be one or the other present in this one. So why am I saying this? Because when you're choosing your models trying to fit to your exact system, if there's existing knowledge, you can directly use it. You need not be worried about, you need not create everything from scratch. No need to reinvent the wheel. Basically, use the existing infrastructure. Same thing I have done for data-driven side of things. I've talked about different kinds of models, reinforcement learning, supervised learning, so on and so forth, so on and so forth. And we also talk about very advanced techniques present in AI side of things, auto-encoding, decoding, so on and so forth, so on and so forth. The idea here is you at least have a surface level understanding on this when someone talks about a digital twin. Now, as I said, this is a typically I spend about 8 weeks, so I obviously I'll not be able to cover entirety in this particular session, but the notes will be shared with every one of you. And I personally feel the simulation which we do after this in the next part will be much more valuable for your own understanding. So let's shift into that part of it. But before we make that shift, we can take a 10-minute break here. So let's do a 10-minute break. And once we are back, let's do the simulation part of it and spend some time on the HTML file.
Professor, one question, if you don't mind again.
Go for it.
Professor, when you call this physics-based model, are these models very different from the algorithms used in the AI models that we have, the machine learning models?
Typically, yes, because data-driven models will not be like, for example, you're talking about y is equal to ax plus b. That is an equation which will be constant throughout whatever it is. So you have an input x, you will get an output y. Unlike in data-driven models, you will not be able to have this equation. You will only be able to say, with high probability, I think I will get this output. That's it. So that's the only.
Got it. Thank you, sir.
Wanted to show an example which everyone can relate. So I'm doing a digital twin of an hospital simulation. So the reason why I call it a simulation is this is in a way inspired by a project which we have done for a hospital, like creating a digital twin for a hospital, for a local hospital. So we have learned a lot during that stage, and based on those learnings, I replicated that in a digital twin. And that is a simulation, whichever you're looking here. So what's going to happen in this thing, right? Whenever you want to, you can click start and increase the speed to 5x just to showcase what happens. Patients come in, keep coming in, waiting room, triaging area. Some go to treatment, some go to ICU. After that, they go to the pharmacy, and then finally they are discharged. Now, every time this process is happening, in between, there'll be certain times when you have to make a decision suddenly. So very similar to what a real life happens, right? So you suddenly realize one day that an accident happened on the highway, and you have a lot more cases currently coming, which will basically overwhelm your staff. So what do you do? Like, are you going to take the staff, or you're not going to do so on and so forth, so on and so forth? So every time when this decision is popped up, you need to make a choice within the time limit. If not, the system will make a choice for you automatically and in random fashion. And this is to ensure that you progress within sufficient time. You can't be spending infinite amount of time on a decision, but rather you do it in a time-sensitive manner. What I want all of you to do right now is play around with this and actually look at what kind of questions are being posed, what kind of impact is it going to have. Everyone in your own domains, you will be having different objectives which you try to solve. You might be trying to have the lowest financial impact, so lowest cost, or some might be focusing on customer-centric jobs where you're looking at patient satisfaction to be the highest, or you can also be looking at much more like your own resources in terms of nurses and doctors. They need to be having sufficient rest time. So you kind of do these trade-offs over time, and that is what the simulation tries to show. And every time you take a decision, you can actually test the impact, where it will show you what the impact is going to be if these changes are applied, and then you can execute it, and then you'll have the exact thing which is happening there. Okay, let me pause. So reset. I will also show you some other things. There are certain preset scenarios where, like, you can have normal operations, you can have emergency surge happening, staff shortage, or something like a pandemic happening, which will basically change the arrival rate of the patients. And the other parameters, for example, instead of having 3 trial staff, you can keep increasing how much ever you want. Same thing with the treatment staff. Same thing with the number of ICU beds. Same thing with the pharmacist. But do note, even though it doesn't show a constraint on this, in reality, you'll be having a constraint on how many number of ICU beds you might be able to have. Maybe you turn all the beds into ICU beds. Even then, there'll be like maybe 10 beds maximum per hospital or something like that, depending on the size of the hospital. At the same time, I also want you to look at, okay, what are the AI predictions saying? So it says that in the next hour, 34 new patients are going to come. So what does that mean? Do you need more resources? Do you need less resources? And what is it going to cost? Everything is basically trying to like build on the real life thing whichever we have implemented, and thus this is going to be a simulation. What I want you people to do, spend the remaining part of the session, is to just go through this, run, understand different concepts, and raise patients such that we can have a good discussion and learn from each other. So that's the next part. So yeah, start the simulations on your side, see what different actions are going to be provided, and what is the influence of that on financial impact, patient satisfaction, so on and so forth, so on and so forth. And as usual, I'm here if you need any help. More than happy to answer any questions during the meanwhile. Okay?
So, quick question on this.
Go for it.
So I just ran this sample with kind of 2x, etc. So I just get a statement after handling that 3 nurses got in sick, current staff shows signs of fatigue. So I just want to know, where is this coming out? Like, how did it, like, is it from prior history that it is taking, like, how many, like, nurses, if they're working for probably 2 weeks continuously given the overload? So how is it able to detect this?
Typically, when the model is developed, it is based on the experience and expertise from the past, when we learn from, we get this wisdom from the existing sources, like nurses, where we ask them, what is the typical time? Are you like, is it like 12-hour shift or 8-hour shift plus 8-hour shift? What is the time when you feel more fatigue, so on and so forth? In reality, that's how we have developed the model. But for this simulation, some of them are preset, and they, once it crosses that particular threshold, it will immediately show that nurses are having a fatigue. That's the simplest way I could simulate the entirety in this HTML file.
Got it. So basically, you're just kind of, for this purpose, your hardware device, like, if you're working for 20 hours a week, you're going to be kind of stuff.
Yeah. Badr, if you have any question, I think raise your hand. Go for it.
Yes, Professor. Just about the design to collect such a data, to build such a system. Is it something like a year or months or?
Okay, this was a 6-month project for us. So we collected the data over 6 months, but do understand, all of it was already the nurses, the doctors, the hospital admin, everyone already were in the hospital for quite some time. So their experience was also captured in this predictions. So I would say 6-month data is more than sufficient.
What kind of accuracy also we can get from this?
Since in healthcare, typically anything about 60 to 70% accurate models, we accept them because better than flying in blind. But in this particular sense, we got about 86% accuracy, if I'm not wrong.
And I think the more time we collect the data, I think more the accuracy we get, right? For example, 1 year, 1 year. Okay, thank you. Thank
you. Yes, Nashi has some question.
Go for it.
You mentioned this is a 6-month project. Is it already implemented in the the hospital? If it is yes, and is it really a business case? Like, they are getting any benefit based on this AI predictions or the analytical reports generated from here?
Yes, it has. Again, for confidential reasons, I cannot share the exact location of where we have implemented this, but it has been implemented. The idea here was, it was much more from the patient satisfaction perspective. And yes, people got good amount of insights, especially trying to reduce the waiting time in the triaging area compared to other places, and also ensure people will be able to leave the hospital in a sufficient time. Yeah.
Maybe I will tell you, I do not know about Singapore, but in India, we have one of the famous, the eye hospitals. Okay, this is a charity hospital. Okay, so if you go there, for example, when I was, I think you can say like 10 years before, you can say, if I go there, I have to put my whole day for that hospital, because they put all the tests, irrespective of whatever reason you go, and they put all the tests. But just you can imagine, last year, I went on May to the same hospital. They were exactly like this, but it's running live mode. Okay, so when I entered, sir, when you register, it will tell you how long time it takes for each test, and when I approximately can leave the hospital. So in the first initiation itself, they will give this. So is it? But it is not.
It's not based on disturbance, though.
Might be imagine like if they are also
4 hours, 5 hours, because many places in India, if you move away from the cities, the primary hospitals.
Even though this particular generalized one doesn't show it, assumes every doctor can treat everything. That's basically everyone's general physician is what it's assuming. But we do have that while we're implementing in the real world. Yeah. For the question.
Thanks, Professor. So in this case, if I am able to integrate all the patients who are coming in, all their vitals, I'll be able to have an even better system to understand like how many patients might go to the ICU who are in need. So that would be even more effective thing for me. That would like
Definitely. But do note, when you bring in more information about patient, you are stepping into the boundary down. So you have to build that curve into your data flow as such, the process flow as such. That is mapped into it. So sometimes you'll be like, oh, this is spike, then over time it tapers down, or vice versa, according to the use case, whichever you're trying to do. So that probably is what you would have felt. Hope that answers.
Okay, thank you.
Yeah. So Sam in the chat, if we tell the AI to reduce waiting time, what if it does by rushing patients and lowering care quality? This is a very, very nice point, Sam. So I'll tell you how we actually deal with it. There are a couple of problems in this, first of all, right? So whatever you have raised brings in the ethics side of things into picture, wherein like, are we only focusing on efficiency and efficacy while neglecting the patient care? Very good ethical question. So models are models at the end of the day, right? So they are just pure mathematical based equations which follow a certain pattern. How do we ensure these models follow the set quality constraints? That is where we have something called as guardrails. So guardrails basically will ensure that every patient follows a particular way. Let's say a patient comes in with cardiology symptoms. There have to be a certain amount of checkpoints which they need to go through in reasonable amount of time. Obviously, there'll be a lower bound for it and an upper bound. Upper bound is for patient satisfaction. Lower bound is to ensure quality. At the same time, we get apt readings. I'll tell you the one thing on this one, right? I know some hospitals intentionally make people wait after they come to the hospital, because after either driving or using public transportation to arrive at the hospital, typically your blood pressure will be higher than when you stay still for some time. So that is an intentional provision which is done as part of the hospital administrative system to get much more consistent readings in certain vital aspects like heart rate or blood pressure, so on and so forth. So those will be the things which will be acting like our lower bound guardrail. So we ensure the model follows this guardrail such that, to most extent, obviously not to 100% extent, we will not be able to ensure it, but wherever possible, we try to ensure there is a minimum standard of care given to the patient. So that's the way we try to modify the AI to push in the direction which we want it. At the end of the day, right, each of these technologies are tools. The tools shine when they are having a skilled worksman. So the better the person who is using the tool, the better the output would be. And that's something which I firmly believe. And every one of us need to make this attempt to try to use this tool to the best extent in the right ethical manner as possible. That's how I would try to answer this question. Any other questions? Okay. If not, this
Madam.
yeah, go for it.
Yeah. From the beginning, we